quiz, I was very pleased to see the number of people who seem to be on top of things. Obviously, the quiz problems are taken right from homework and discussion, so one has to be able to think independently, particularly on homework problems and exam problems. One needs to be able to think independently. But from what I'm seeing, it looks like people are getting on top of understanding energy levels and mechanisms, and also curved arrow notation, which are all some of the very important aspects of reactivity. So the reaction that we discussed in the quiz, the first reaction, was an SN1 reaction. We brought in the concept in chapter 6 of SN1 reactions and SN1 reaction mechanisms. And we introduced it by name, and then we said that stands for substitution, nucleophilic, unimolecular. We took a little time to discuss the energetics of these reactions and some curved arrow mechanisms. What I'd like us to do today is to continue our discussion of SN1 reactions and to focus on mechanistic and stereochemical aspects of these reactions. I want to start us off with a simple reaction, a Solvolysis reaction, kind of similar to the one that we had in the problem, in the sense that you start with a tertiary alkyl halide. And in fact, I've chosen a tertiary alkyl bromide as an example. So let's take 2-butyl bromide, 2-bromo, 2-methyl propane, and let's carry out the Solvolysis reaction on it. And by that I mean let's dissolve it in a polar solvent containing some water. Solvolysis is cleavage by solvent, solvo, solvent, lysis, cleavage. And so we'll use water as a solvent here. And like so many organic compounds, they don't dissolve very well in pure water. So we're going to add a co-solvent that mixes with water. And that co-solvent is acetone. We talked a little bit about acetone when we talked about ketones and functional groups, nail polish remover. Acetone is a very polar molecule, mixes with both water and organic molecules, so it can bring them together. It's going to be a spectator here. Under these conditions, we get one major product from the reaction, and that's 2-methyl 2-propanol. So I'm going to write major product here. This is the product of an SN1 reaction. You'll also see a little bit of a minor product, and we'll be discussing this more in the next chapter. This minor product is 2-methyl propene. I'll write minor product. It's getting a little crowded here. I'll write it as prod. This is a product of an E1 elimination reaction, so I'll write E1. You're going to learn more about that in chapter 8. I'm going to put this in parentheses. Right now we're not going to pay any attention. Only a little bit of this is generated, but we're going to see in the next chapter how this is formed. I want us to take a moment to look at this reaction and to look at, first of all, the overall reaction, and second of all, the mechanism. As I said, organic chemists are very organocentric, and so even though I haven't written any other reactant here, and obviously oxygen comes into play, we're getting it from the solvent. This would be one way you'd see an organic chemist write this reaction. For the sake of teaching, for the sake of helping us think about things, let me write a balanced equation, and that will give us a basis for a further discussion. So here's our tert-butyl bromide. It's going to react with an overall reaction of 2 water molecules. So I'm going to write 2H2O. and we're going to go, if we want a balanced equation, we're going to generate tert-butanol. Again, we're going to forget about any minor E1 product right now. Plus aqueous HBr. You could write it as HBr and just show one water molecule, but in reality HBr and water dissociates. So I'm going to write H3O plus Br minus. Let's take a look at how this reaction occurs, because this is worth thinking about in some detail and also give us a chance to review curved arrows and reaction mechanisms. So here's our tert-butyl bromide. I'm going to try to be good, at least for the moment, and write a nice full mechanism showing all lone pairs and all atoms and all bonds. So just like in the problem on today's quiz, the bromide can leave, giving rise to a tert-butyl carbocation. Bromide anion. We have lots and lots of water present. Water has electrons. Water is willing to share those electrons. The tert-butyl cation desperately wants electrons. It doesn't have a complete octet. In other words, our water that's present in great abundance can go ahead and attack the tert-butyl carbocation, and I'll draw a curved arrow flowing from the electrons on water to the carbon atom of the carbocation. Now everyone has a complete octet. We have positive charge on the oxygen. In water, protons come on, protons go off. When I have H3O plus in water, that H3O plus is constantly exchanging protons with other water molecules. And we have this huge abundance of water, so water can take a proton off of our intermediate here, just driven by mass action. So I'll show our water molecule, another water molecule coming in with its lone pair of electrons. Arrow electrons flow the arrow flows from the electrons to the proton, and in turn we put our electrons back onto the oxygen. Here's our tert-butanol and our H3O plus. I'll point out, although I haven't written this, that this is a very common reaction. And remember how I made an analogy between water and methanol? I could write exactly the same equation. Tert-butyl bromide in methanol gives rise to tert-butyl methyl ether, OCH3, plus CH3OH2 plus Br minus. You should work that out on your own. It's good to think about, because all of these reactions have these tremendous analogies among them. What I'd like to do at this point is to take this idea here and to bring it to some ideas about stereochemistry. So I'm going to talk about the stereochemistry of SN1 reactions. And in looking over your chapter, I thought that chapter 7 was a little bit more jumbled than some of the other chapters. And so what I've done is, rather than giving a different example, I've just taken an example right from your chapter to help us walk through that example. Let's take a chiral tertiary halide, and the one that I'll take is 3-chloro-3-methyl hexane. And I'll start with just the S enantiomer. So this is specifically S3-chloro-3-methyl-hexane. This is a little bit of a contrived example, but it's one that I think didactically works, so I'll use it. So let's draw in our stereocenter here. Chlorine and methyl. And you can check over it with your own knowledge of how to assign conical Krylov stereochemistry and make sure that I got it right in writing it out as the S enantiomer here. And let's carry out the same type of solvolysis reaction. I think I'm borrowing the conditions from your textbook, and they just show water here. They show it above the arrow as a reagent. Same whether you put it above or below the arrow. And let's apply a little bit of heat. It's not surprising that heat speeds up SN1 reactions. In going to our intermediate, remember this first step is the rate determining step in our SN1 reaction, the ionization. As we're going from our intermediate to from our reactant to our intermediates, we're going from one particle to two particles, namely from tert-butyl bromide to the tert-butyl carbocation and bromide anion. So there's an increase in entropy. Remember that delta G equals delta H minus T delta S. If you have an increase in entropy, or delta G double dagger if you want for an activation, but we'll take it as delta G. If you have an increase in entropy, that T delta S step is going to become more negative, or the S is positive, so minus T delta S is negative. That's going to in turn lower the activation energy, lower the energy of that step. So this heat speeds up this reaction. What we observe from this reaction is two products, or more specifically the racemic compound. I'll just draw this out as one enantiomer plus the other enantiomer. So just like in our bromide reaction, we're solvolizing to the alcohol here. But now we get two products. One is the product occurring with retention of stereochemistry, and the other is the inversion of stereochemistry. And they're formed in precisely the same amount. In other words, a one-to-one mixture, that is, we're racemic at this point. So whether we had started with the S enantiomer, whether we had started with the R enantiomer, it wouldn't matter. We'd get, in both cases, the racemate of the resulting alcohol. The reason this occurs is that we're going through a planar carbocation intermediate. As soon as that first step occurs, we've lost all stereochemistry. Let me show you what I mean. So our first step, our ionization step, takes us to a carbocation that's now completely flat. So this is planar, it's achiral. Remember, if you're a planar molecule, obviously you have a plane of symmetry. And so all of our stereochemistry is gone. Now, just as we saw in the case of our SN2 reaction, when you come from one face or another face, you generate a new stereocenter. Now we have our water coming in and attacking. If it comes from the front face, you generate one stereochemistry. If it comes from the back face, you generate the other stereochemistry. Let me show you what I mean. here is our carbocation. If we have our water, and I'm not going to write out any detailed mechanisms at this point, but if our water comes in from the front, now when we generate a bond, we have reformed the stereocenter. We've generated one of the enantiomers. On the other hand, which face the water attacks from is completely 50-50 chance. The front is identical to the back. Water doesn't see any difference in the front and the back. If water comes in from the back, in the same way, and of course, by back, I mean from behind the blackboard. I can't represent that very well in 2 dimensions here, but I'm just going to say from back. Now, when we form our stereocenter, we formed it like so. And then in water, as I indicated in our central blackboard, protons go on, protons go off. A water molecule simply takes off a proton. I'll say minus H plus, which is a shorthand that I'll often use in writing less detailed mechanisms to imply that a Lewis base, like water, has taken off the proton. So minus H plus takes us to the alcohol with the OH pointing out of the blackboard. That happens to be the R configuration of the alcohol. And here, minus H plus takes us to the alcohol with the OH pointing back into the blackboard, and that happens to be the S configuration of the alcohol. Actually, no, wait, this is the 1, 2, 3. This is the S configuration, that's the R configuration. All right, thoughts or questions at this point? The chlorine becomes an ion, yep. So, you mean the first and the second? Okay. So, very good question. The question is, why did I write this way here? So remember I mentioned that organic chemists often just focus on the organic product, and then we have many different ways of communicating the same thing. So the first equation, I just focused on the organic product. Second equation is the first step of the mechanism where I've generated chloride. If I wanted to write an overall balanced equation, just as we had done with the terpyl bromide, I'd say that 1 molecule of the terpyl chloride plus 2 molecules of water generates 1 molecule of the alcohol plus H3O plus Cr minus. Some people might also write that as 1 molecule of the chloride plus 1 molecule of water goes to the alcohol plus HCl, which is similar, a little less correct, but you would see it also written out. Other questions or thoughts?
How does the CH3 change from the front to the back?
How does the CH3 change from the front to the back? Meaning in the course of the reaction?
Yeah, then what's going to receive the part?
Pardon?
And what's
Okay, so, very simple. I am the molecule, and I started with the methyl group. How did I do it? Methyl group behind, in front, and the chlorine going behind me. The chlorine leaves. The chlorine is this piece of chalk. The carbocation goes coplanar, like this. Water comes in, and water can come in like this, or water can come in like this, and it's Because unlike me, the carbocation really is achiral. It's completely arbitrary. Once the water comes in, we start to form a bond. As the bond forms, we go back to a tetrahedral center. In the case where the water is coming in from the front, we form a tetrahedral center with the OH sticking out. In the case where the water is coming from the back, we form a tetrahedral center with the OH going back. Other questions? You can get very amusing demonstrations out of it. Please repeat the question. That's the first step of the reaction. Yeah, the bottom blackboard is the first step of the reaction. Pardon? Oh, we're getting OH back in OH. Oh. Now I understand the question. I simply arbitrarily and without intention drew one enantiomer here and the other enantiomer over here. And as I said, this was a little bit of a contrived example because you would never really isolate one enantiomer or the other enantiomer. If you prefer, let us, for the sake of clarity, let us re-annotate this, and we'll do it like this. So either of these exists as the case. Since, as I said, this really is a very, very contrived example. If I could get one pure enantiomer or the other, we would see loss of that stereochemistry. And in fact, what would happen would be if you took the racemate, you would generate racemic alcohol. So if you started with a mixture of the enantiomers of the chloride, you would generate the racemic alcohol, but it wouldn't be as if one enantiomer went to one enantiomer of the alcohol and the other went to the other enantiomer. We call this process loss of stereochemistry. All right, let's take a look now at some of the mechanistic aspects of the SN1 reaction. Specifically, let's look at the kinetics of the SN1 reaction. We've already talked about the kinetics. We said that the first step is the rate determining step. So the ionization here is the rate determining step in an SN1 reaction. What the implication of this is that the rate of reaction depends only on the concentration of the alkyl halide, only on the concentration of the electrophile. Rate is equal to K times concentration of the alkyl halide. So, just for the sake of variety, I'll show you another reaction. This is one very similar to what we talked about before when we used our example of cyanide attacking. If we have bromo-triphenylmethane, and we carry out a very similar solvolysis reaction in aqueous acetone, it shouldn't surprise you that we get triphenylmethanol, PH3COH. Same example, very similar example I used when we introduced SN1 reactions with cyanide. So in this particular example, our rate is going to be the concentration directly proportional to the concentration of bromo-triphenylmethane. Now, let us imagine a number of different situations that might come up. And this is going to lead us into our discussion for the last lecture of the quality of various types of nucleophiles. So I'm going to write some data from an experiment that one could do in your laboratory course. And in this experiment, we're going to look at the effect of various nucleophiles on the rate and product of reaction. All right. First example, let us imagine that instead of having water present, we still have water, we still have acetone, but we add some sodium azide. So I'm going to say 0.1 molar NaN3, sodium azide, still water and acetone as our solvent. So we've thrown into a flask, let's say 50 milliliters of water, 50 milliliters of acetone. We've dissolved our azide to make a 0.1 molar solution, and we throw in, let's say, a gram of bromo-triphenylmethane. What we would observe as a product is triphenylmethyl azide. But what's interesting is that the rate of the reaction is the same as the rate of hydrolysis. I'll say as above, referring back to our reaction here where we're carrying out our solvolysis. Let's take a look now again in this experiment. This is what you would observe in the laboratory. Let's take this same reactant, and we'll take sodium azide, but we'll double the concentration of sodium azide. So now everything's the same except we're going to use 0.2 molar sodium azide, NaN3, in aqueous acetone. And it shouldn't surprise us that our product of reaction is still the same azide. What may surprise us until we think about it is that the rate of reaction is same as the other ones. And let us continue in trying to understand this chemistry. Let's imagine now that instead of using sodium azide, we use sodium hydroxide and sodium azide mixed together. So let us take a 0.1 molar solution of NaOH and 0.1 molar solution of NaN3 of sodium azide in aqueous acetone. Now we get a new product. It's not the azide. We're back to the triphenylmethanol, PH3COH, but the rate is the same as above. In other words, all of these examples, whether it's the hydrolysis in pure water, whether it is the SN1 displacement by sodium azide, at 0.1 molar, whether it's the SN1 displacement by sodium azide at 0.2 molar, or whether it is the competitive SN1 displacement with sodium hydroxide and sodium azide that leads to the alcohol, all of these proceed at the same rate. This tells us something about our nucleophiles, and it also tells us something about the mechanism. And indeed, it's through reactions like this that chemists learn how these types of reactions proceed. Remember, in this reaction, formation of the carbocation is the rate-determining step. Then the carbocation gets trapped. In other words, what I'm saying is we have PH3CBr. In the slow step, in the rate-determining step, it ionizes to the carbocation plus bromide. Then a nucleophile comes in. And that step is fast. And it gives rise to whatever the best nucleophile is available that's bound to the product. And we've just seen this competition. There are 3 different nucleophiles present. There's water, there's sodium azide, and there's sodium hydroxide. In the first experiment, only water is around. It's the only nucleophile that can come in and trap. So it traps. As soon as you throw in sodium azide, the sodium azide competes better. The azide is a better nucleophile than water. When you pit sodium hydroxide against sodium azide, now the hydroxide competes better than the azide. Hydroxide is a better nucleophile than azide. So we can rank the strength of our nucleophiles as hydroxide is better, is greater than, azide is greater than water. We can show this diagrammatically with an energy diagram very similar to the energy diagram that you made in today's quiz. Now in today's quiz, we had exactly the same product as reactant, with the exception of an isotope label. In other words, the 2 products were exactly equal in energy. Here, in all cases, we're going downhill. And so I'm going to diagram this out very much like you did on today's quiz. Here's our reaction coordinate. Here's our energy. Draw an arrow going up. On the left-hand side, I'll show our reactants, our bromo-triphenylmethane, and I'll write our generic nucleophile because we're going to make some comparisons among nucleophiles. On the left, on the right, I'll show our products, lower in energy, PH3CNU plus Br minus. And I'll show our intermediate in the middle, and the intermediate is higher in energy, of course. It's the carbocation plus bromide plus Nu minus. And we go over the highest energy barrier. Our rate determining step is determined by the height of that barrier. We go over the highest energy barrier. And then in going to our product, we go over a lower energy barrier to get to our product. When we're competing two nucleophiles, one against the other, now we can have, let's say, one barrier for azide, and hydroxide, which competes better, has a lower barrier. So I'm going to write with a dotted line a second step showing a lower energy barrier for OH minus. And of course, if I were showing water, it would be still higher. So the point is, in the rate determining step, we go over a high barrier, we form our carbocation intermediate. Nucleophiles then compete. It doesn't affect the rate of reaction. If azide is present, we form the product with azide. But if hydroxide is present, a lower energy pathway occurs that gives us rise to the alcohol product. Okay, next time we will pick up discussing